So LeetCode number 1283, find the smallest divisor given a threshold. So you're given a threshold and you need to find the smallest divisor so that summing all of the array elements divided by your divisor gives you a result that is less than or equal to the threshold. And whenever you do a division of an array element by your divisor, you need to round it up to the nearest integer greater than or equal to that element. So the ceiling or the seal of the result of that division. So I just pasted in the code for our binary search template because this lends itself very well for that template. So remember that I've already shown you a lot of times this problem on this kind of template on my channel. So this gives you the smallest value that satisfies a function that you need to implement. So yeah, we're just going to have to change these three values as usual. So left, right, and the feasible function, right? So the reason for which you can use a binary search on this problem is because if you find a divisor, let's call it x, for which this statement holds, then any divisor greater than that is also going to work. And if you find any divisor for which this is false, so the result is above the threshold, then any divisor smaller than that will also not work. Okay, so that's the reason for which we can use a binary search. And any problem where you can find such a observation will also work with binary search. Okay, so now we also need to do these values. So this is the search space, and the left bound is just going to be 0 because the divisors need to be positive, and the right bound, we need to think about what is the biggest possible value that can be the solution to this problem, given that it is guaranteed that there will be an answer. And for this problem, the right bound is actually the maximum number in the array. And that's because when you divide all of the numbers in the array by the maximum number in the array and you seal them, you always get 1, right? So the sum is just going to be 1 times the number's length, and you can't do any lower than that. So you know that this is the correct right bound. Because even if you take like 9,000 or something, you're still going to have 1 because you're sealing all of the division results, right? Okay, so now we just need to implement the feasible function. So once again, remember that this is going to return, when we return left here, we're going to get the smallest number that satisfies, so for which this feasible function returns true. And that's because when you do this here, you only increment left, you only update left whenever it doesn't work for mid, right? So if it is not working for mid, so if it is not feasible with mid as a parameter, then you set left to mid plus 1. So you're always certain that left is the first one for which it works, because you're incrementing mid by 1, and you know that it doesn't work for mid, okay? So yeah, now we just need to implement that feasible function. So what we want as a feasible function is we want to return if it's working. So if dividing all of the array elements by this divisor returns a result and summing them up has a result that is less than or equal to the threshold. So yeah, we just start with a sum of 0, and then we loop through all of the numbers in the array. We divide them by the divisor, and we take their seal. So the nearest integer that is greater than or equal to the division result. And then we add it to the sum. And if at any point the sum is greater than the threshold, then we can straight up return false. But if we never return false, then it means that this statement is holding, so the condition is met, and so we can return true, right? So yeah, I'm going to submit a solution to show you that it works. And the time complexity for this is O of n times the maximum of the numbers. And that's because our search space is initially large, like this minus this, which is just maximum of numbers. And at every step, and sorry, obviously I meant log of max of numbers. So at every step, we halve the search space. And so at the end, we're going to have log of the initial search space size. And for every time we do an iteration here, we call a function that takes n time to, possibly takes n time to calculate. So yeah, that's the worst case scenario. And the space complexity is just O of 1 because we do not have anything apart from the input, no weird data structures or anything like that. So that's it for me today. Thank you for watching, and bye.